Hello, so this is part two of the same lecture. Okay, so suppose I have, this is my data, or maybe there are even actually other columns too. And there are, here there's only 8 rows. I've reduced it. In the original data, I think there's 522 rows and something like, I don't know, 11 columns or something like that. So I've just reduced it to these, for now, these 3 columns, and just took out 8 of the rows. I think the first 8. The first column is price in thousands of dollars. This is for residential property. The second one is square feet of the house or building. And the third one is square feet of the lot. And we would like to consider the price, the response, and look at X1 and X2 as candidates for predictors. So if we do that, I pre-wrote this out, so I think this makes sense just to use this, sort of writing it out. Sometimes we'll write it out, sometimes not. So say I want to, I'm first checking to see how good of a model it would be just to use the square feet of the building. So just to use X1. So I make my model mod X1 with the LM command, and then I have SSE X1. I get 12.5 billion. Okay, so 12.5 billion. What are the units here? Well, the units should be, I think, dollars squared, right? So this is like 10 to the 10th, right? It's about 10 billion, so about 10 to the 10th dollars squared, right? Because I'm taking SSE is the sum of the errors. So the sum of the distances away from the regression line squared. So I get about 10 to the 10th here, or yeah, I get 12.5 billion. So on average, what do I have? If I divide by 8, I get roughly 1.5 billion per data point, and if I take the square root of that, I have something along the lines of what would it be? 1.5 billion. What's the square root of 1.5 billion? Well, let's see, that's 10 to the 9th, so 10. So it's going to be something along in the tens of thousands. So this might make sense for that data, right? Because you had prices that were like in the 360, 340, 250. So the line could be off by in the tens of thousands. So it looks right. Okay, so anyway, this was done by the computer. I get this for SSEX1. Now, say I want to try both. So I'm going to put in X1 and X2 in here. So this is R for how to do this. I don't think there have been any MLR examples, or maybe there was one right at the end before we stopped. So you just write a plus sign. It doesn't mean add the predictors together. It just means use these 2 predictors in a linear model. So we have mod X1, X2 is LM Y squiggle X1 plus X2. So it uses both those 2 sets of vectors, both those vectors of 8. And again, now you can get SSE from R. You could do it by hand too. Once you have your B0, B1, and B2, your estimators. And it goes down, right, which is good. So it goes down to about 11 billion. So it went from 12.5 billion down to 11 billion. So you get some improvement, but again, you've made your model more complex, and you've lost a degree of freedom. So is it worth it? That's the question. So SSR x2 x1 is just simple definition. It's just the difference of these two. So it's about 1.5 billion here. Okay. I can think of this as a general linear test approach, where the full model is the more precise model with the lower SSE. This is the first one labeled F here. And then the reduced model is this one, just the SLR model. And under this, if we think about this way, then we have F star is equal to, I take the difference of the two SSEs, the reduced minus the full on the top, and I divide by the degrees of freedom. The difference, those are additive as well. And then I divide by the full model divided by its degree of freedom, and I can rewrite these now using my extra sum of squares notation, because the top is clearly an extra sum of squares. It's SSR x2, the amount of explanation I get when I add x to the model given x1. And the degrees of freedom of that extra SS is 1. The reason you know it's 1 is from the step before, because you know those two degrees of freedom are additive. So they're additive actually under the null hypothesis that they're not, that the extra coefficients are 0. So it's a little complicated. We can actually do those proofs, but we have the skills to do them. Maybe we don't actually. So we need to do a lot of linear algebra, and it doesn't seem to pay. But we've been doing these problems for a while now, and we've accepted that these are F distributed. What happens is, under the null hypothesis, the numerator and the denominator, if you divide each by sigma squared, you get 2 chi-squareds divided by their respective degrees of freedom, so you get an F distribution. Okay, sorry about that detour. I can't help it. I maybe do a lecture on this. I'll actually do the proof for you on one of them, and then you don't have to watch it. It's different than when I'm in person, right? I can do stuff like that now. So anyway, if we go here and you accept this additivity rule from the general linear test approach under the null hypothesis. So here, I wrote it down after here. We have this is equal to, so it's kind of a backwards statement, almost you should read it from the bottom. Okay, we have SSR x2 given x1 over its degree of freedom, which is 1, divided by the SSE of the full model divided by its degree of freedom, which is 5. And then you can use the mean square notation, MSR x2 given x1 over MSE x1 x2. And this is F distributed with 1 and 5 degree of freedom under the null hypothesis, which in this case is beta 2 equals 0. There is not, well, and then HA would be beta 2 not equal to 0. Okay. In this case, what do we get? We get F star is 0.748. Remember, we subtracted the top and we got 1.6 billion, only 1 degree of freedom. On the bottom, the total was something like 12 billion or 12.5 billion, but we have 5 degrees of freedom in the full model. We divide by that, it reduces it, and we get F star is 0.748. Now, okay, so how does this do? Well, let's find the 95th quantile for the F15 distribution, and if I do that, I get 6.6. In other words, if I look at an F PDF, say this is F15, then I want this is 0.95, this would be 6.6 right here. Okay, and our data, our F star is way over here, right? It's Here's F star, 0.748. So this is not in the rejection region. In other words, we would like to bound the probability of a type 1 error to be 0.05, say. That's what I picked here. And if I do that, then I reduce the probability of a type 1 error to 0.05. So I set my test up this way using the likelihood argument. I say, well, if F star has to be bigger than 6.6 for me to reject it, and it's not even close. So lot is not significant in reducing price variation if building is already in the model. That's the English for what we just did. So we accept H0 in this case.